Right, well, see how well this comes out. It's a bit hard to tell on these tiny camera screens what you're looking at, but it seems like it's okay. So anyway, been knocking up some ideas for a guitar amp, reading some books, going over some bits and bobs. Anyway, been chucking some ideas back and forth with a few friends of mine who play guitar, and they reckon having a simple compressor on the output, so the actual what's coming out of the speaker end, and then being attenuating at the master control. So if you really start pushing it, it's not affecting what's going through the preamp, it's just limiting what's coming out the output of the amplifier. So I have just been playing around in here. I hope I've got autofocus on. I seem to think I do, but looks to be focused. So I've come up with this pretty simple schematic. So LDR, I think that's how you draw an LDR, LED combination. These are sitting in the same package, you'll see that in a bit. They're just two devices with some heat shrink around them. So signal comes in via a 22k resistor, then it sits in parallel with the LDR to 0V. If you remove the pot, the LDR will connect to 0V. It's essentially in parallel with the input resistor. I know it looks like it's in series, but for the signal it sees it is in parallel. So it can shunt signal off to 0V. There's another potentiometer here. So these two potentiometers, this one is the threshold. This allows you to adjust the point when the compressor comes on. This is the level. So what's the attack? I don't know what you call it. The depth. There's so many different terms, but so this one at which point the compressor kicks in. This one then how much ultimately the compressor will actually allow it to attenuate the signal. Because I'm just using my signal generator in a minute, I've got a gain stage here with a gain of 4, 5-ish, whatever it works out to. That's upping it. There's a 1N4, 148, that rectifier, halfway rectifies it again. In the final one, I'll probably put a full bridge rectifier in there. You don't have to worry about a precision bridge with no voltage drop because it's coming from a loudspeaker output. You're not going to want the rectifier to kick in until it's pumping up some volume to some degree. If you do, again, you can just put a gain stage in here, so it doesn't matter. But to be honest, even halfway rectified, it would still be pretty useful. The chance of that somehow one half wave of the signal is going to be considerably higher than the other is pretty slim. It's going to alternate between the two. So yeah, it's probably just leave it like that, to be honest. This is the decay timing circuit. So there's a 470 microfarad capacitor with a 100k resistor in parallel with it. So this op amp can charge this cap up near instantaneously through this diode. However, even if the signal dies, this cap takes a certain amount of time to discharge. It stops at, it's what's called pumping, where on the compressor, if there's a loud transient, the compressor will kick in, drop the level down, then because the levels drop down, compressor kicks out, level rises quickly, compressor kicks in, drops out. You get the cyclic. It's really annoying. You'll hear it in a lot of modern music. If there's a beat or something or a loud point, it starts loud, quiet, loud, quiet, loud, quiet, and it's just an annoying pumping sound. Adverts are terrible for it. And there's just the op amp driving the LED. So if we come and look at what's on the bench over here, so I'm going to have to move you in a bit. Awesome camera work. So here is the circuit. Shows how long I've played around with some breadboard stuff. Here's the old clock that can't be set chip still here. So as you can see on the bench here, it is just a mess, really. I've got a transformer, which is dual rail supply for the op amps. I've got my signal generator over there. I've got this scope going over here. We'll look at that in a bit. I've got my multimeter showing the voltage which is coming out of the limiting circuit. So this little black package here, if you'll be able to see it, that little bit just there, that's an LED rammed up against an opto isolator. There's the op amps timing circuits. So not really a great deal to see there, but the interesting thing really, if I pull you back now, so is going to be, what's that? I'm looking at my speaker over there. Screen's backwards, isn't it? So it's going to be what's happening on the scope. So as you can see, the blue is what's coming out of the compressor, the yellow is what's going in. So if I kill the blue, because the blue is on a different scale, it's sort of this scope has a slight offset as you drop between scales. So I've got the compressor at the minute set on its highest attenuation, so I'm going to get it so it just kicks in. So if I can get the meter in shot, let's put the solder behind that. So you see the breakover voltage on the LED, red LED, somewhere about 2 volts I think. So if I start upping the level, so you can't, what's coming out of the compressor is unchanged. I'm upping the level of what's going into the actual detection circuit, and you'll see at some point, so you see the LED must just be starting to glow at 1.5 volts. The blue is dropped down a bit. If I keep cranking you can see the levels right, and even though I'm now really cranking the, you can't really see, so I can get a bit more in, even though I'm really cranking this control, and the voltage change needed is so minor because I've got the depth turned up so high that it really just can't rise a great deal above where it is. But if I just tweak it down a bit to there, so I'm going to lower the depth right down now. So here's the interesting thing, look, even though the depth is being lowered considerably, because it's in a whole feedback circuit, the higher the output goes, the higher the light turns on, the more the input is attenuated, and so on. And the opposite is true. If the light goes off, the higher the input to the compressor circuit goes. It sort of hits an equilibrium where even though you alter the depth, so the amount it can actually attenuate the signal, as you lower that, because the detection circuit itself is unchanged, the compressor just works a bit harder. But so if I just tweak the depth so it's on a bit, what will happen now, as you can see, massive rise in voltage now, but this signal cannot go any lower than that. So that's compressor off. Let's get the compressor just kicking in. And so again, 1.5 volts. If I crank the depth right up, you see again the voltage dropped, but the actual signal didn't drop a great deal. As I turn the depth down, you can see the voltage just rises. It's just the interesting thing with compressors. That goes back to what I was saying about needing to slow the time decay down, otherwise it would just start oscillating on, not so much on a constant signal because it's fairly constant, but on loud and quiet transients it would not be overly effective. So yeah, and you can see if I start to crank the depth up, you'll notice the voltage goes down and the signal itself isn't going down overly rapidly now, because as I'm cranking the depth up I'm just getting more and more attenuation at the input, and you can see that the voltage actually is just dropping down to compensate. I would have to start cranking up the input signal, and you can see the actual, there's a limit on how much it can attain. You can see I can alter the signal quite a lot, and the actual signal coming out of the compressor doesn't alter a great deal, but you can see it sort of starts getting a bit wobbly because it's working hard at this point. So yeah, obviously that, to be honest, this one sort of gives you more of an idea what's going on, because you're actually seeing the signal coming in. This one, you're not really seeing what's going on out the compressor at this one. So I will knock the depth down again. Now you can see on that one, look, the signal is staying fairly constantly attenuated until it drops a lot, and then it comes back. But yeah, simple enough. So yeah, so that's quite interesting. If you sort of adjust the threshold to just kind of there, so look, massive adjustments of the depth don't really do a great deal. More, and see that even though the threshold voltage is changing there, it doesn't need to do a great deal of compressing because it's holding the output fairly constant. It's already attenuating the signal as much as it can. So it's trying to, as the voltage rises, it's trying to attenuate the signal more, but it can't. I need to increase the depth of it, and again, like I keep saying, you then end up with a scenario as you start to drop the threshold level down, well up, it's still, so it's not till about there. You can sort of see that better if I do it, like I say, do it this way. You can see now the threshold is there, and then as I start trying to increase the input more, to be honest, that's a far better way of so yeah, that's the threshold has been met. As I start increasing the input, so you can see, because I have the depth quite high, it can do a pretty good job of holding the output. However, if I decrease the depth, as you can see, it can't attenuate the what's coming out of the compressor the same degree. So yeah, I just nerd talk, tech talk, nerd talk. It's working as it's meant to. So yeah, it took about half an hour to actually knock up. A little bit of sucking on the old vape and thinking about, but I think I've rambled on a bit, but I kind of got the gist of what I'm trying to say across. So yeah, that works. That works very well. So yeah, just another quick video from me. Just like I say, another half hour on the workbench playing that. It's fun to play about. Gets you off the sofa just watching Star Trek on Netflix, doesn't it? So yeah, anyway, as always, thanks for watching and catch you again.